Welcome to the Physics Almanac. In this video, we will be continuing our analysis of orbital motion, and we will be looking at angular momentum. Is it conserved? And if so, for which observers? I've rated the physics level in this video as intermediate. Let's first recap a few important properties we discovered when we derived Kepler's laws of planetary motion using Newton's laws of gravity and his laws of motion. We're going to need to use some of those results for this video. Our setup was a two-body system, so we had two masses, m1 and m2, and we picked an arbitrary point as our origin, with the one condition that the origin be in an inertial frame, meaning a frame that's not accelerating, because Newton's laws of motion are from the point of view of inertial frames. We called the positions of these masses r1 and r2, these are vector quantities, and we called the vector between these two masses r, which is just equal to r2 minus r1. This is the position of mass 2 relative to mass 1. And we assume that the only force between these two masses was the force of gravity. We then plugged this into Newton's laws of motion and solved it to find that the relative position r traced out a conic section curve. Which conic section the orbit followed depended on the eccentricity e. R minus is the point of closest approach. It's the minimum r between these two masses, also called the periapsis point. And phi is the angular position of this vector r, and it's measured from the periapsis point. So you can imagine as these planets orbit one another, the position r will change after some time, and that change in angle is what we're calling phi. If you'd like to see in detail how we got this result, you can watch my video on Kepler's first law of planetary motion. Along the way in this derivation, we also found that the quantity r squared d phi dt was equal to a constant, which we called little l. And little l had the following value, where capital M is the total mass of the system. It's m1 plus m2. In the case of a closed orbit, so a circle or an ellipse, you could also rewrite this using the semi-major axis. And finally, and what's important for this video, is that we show that this is equal to r cross the velocity. So the position r times the velocity associated to that position, meaning the time derivative of this vector r. R cross v is in fact related to the angular momentum, because the angular momentum is m times r cross v. So this quantity is sometimes called the specific angular momentum. It's the angular momentum divided by the mass. But which mass? Well, that's what we're going to find out in this video. And we're also going to check, is there any other angular momentum in the system we have to consider? Finally, another important result we found was that the center of mass velocity was constant, so long as the observer is in an inertial frame. The center of mass velocity is just the time derivative of the center of mass position, which I'm going to call capital R. Now, the center of mass position is a more useful coordinate to use because everyone agrees on its location. It's located along this line, somewhere in the middle. Where exactly will depend on the relative masses of m1 and m2. Likewise, the coordinate r is also more useful to use because it's just the relative position between these two masses. So we're going to do a change of coordinates. Instead of using r1 and r2, we're going to invert these two equations to get r1 and r2 in terms of the center of mass position and the relative position. I'm going to spare you the algebra here. It's fairly easy to figure out, but I encourage you to do it for yourself just to verify. Okay, now that we have our initial setup, we're ready to check out the angular momentum of this system. Angular momentum, which I'm going to call L, is defined in the following way. It's the position crossed with the momentum. Cross means the cross product, the vector cross product. This means you're picking out the component of the momentum that is perpendicular to the position. And it's a vector, and it points perpendicular to both the position, r, and the momentum. In this case, with a two-body system, we have planar motion, so r and v are in a plane, so the angular momentum will point out of the page, or out of your screen, or possibly into your screen, depending on if it's positive or negative. Now, we only have two objects to worry about, so our sum is only going to be two terms, the angular momentum of m1 plus the angular momentum of m2. But remember, we don't want to use R1 and R2, so we're going to substitute our coordinate change into this equation. If you're finding this video helpful so far, please take a second to like and subscribe, maybe share it with a friend or colleague. And if you'd like to support the channel, I invite you to go to my Ko-fi page. There'll be a link to it at the end of the video. You can also find it in the video description. We now have to FOIL these two terms out, and I'm going to group all the like terms together. So here we have the two terms with R cross V, capital R cross capital V. That's going to be this term here, multiplied by M1, plus this term multiplied by M2. So we have M1 plus M2. Then it turns out that the cross terms, both of them, the capital R cross little v and little r cross capital V, actually have the same factor in front of them. So I can group those two together. And for the first term, that factor is negative, and for the second term, it's positive. So the cross terms all cancel out because they're multiplied by 0. And finally, we have the final terms, the little r cross little v terms. Well, M1 plus M2, that's just capital M. And the second term here simplifies to what's called the reduced mass, which is equal to M1 times M2 divided by the total mass. Okay, let's analyze this result a little bit. This first term is the total mass of the system times the center of mass position crossed with the center of mass velocity. This is just the angular momentum of the center of mass. This term has to do with the angular momentum of the relative positions of these masses because it's the relative position crossed with the relative velocity. So you can think of this like these two bodies are in a big box, and this term here is the angular momentum of that box. You don't know what's in the box, you just see this box moving, and it's got some total mass m, a position capital R, and a velocity capital V, and this term is its angular momentum. The relative term, which is the orbital angular momentum, is what's going on inside the box. So the box is moving past you, it's got some angular momentum, and then inside the box, these two bodies are going around each other, and so that's what this term is. It's the angular momentum associated to the motion inside the box. Now recall from the beginning of this video that we already know that R cross V is a constant. It's equal to little l. So this is equal to the center of mass angular momentum plus mu times little l, which is the orbital angular momentum. But wait, there's more. We also know that V is constant, so long as the observer is in an inertial frame. Therefore, the center of mass angular momentum is also constant, and so the total angular momentum is a constant. It is conserved so long as the observer is in an inertial frame. And in practice, we generally make our life easier and take the point of view of the center of mass, which makes this term LCM go to 0, giving us that the angular momentum from that point of view, from the center of mass frame, is just the orbital angular momentum. But what if you're not in an inertial frame? What other observers are going to say angular momentum is conserved? After all, if we think of an Earth observer, say we take the Earth-Moon or the Earth-Sun system, we're standing on one of these bodies. What we really want to know is, what are we going to see? And these bodies are moving around one another, so they are not inertial observers, at least according to Newtonian gravity. Some of you may be saying, wait a minute, in general relativity, orbital motion is inertial motion, but here we're going to take a Newtonian perspective. In general relativity, the conserved quantities are slightly different as well. So I'm not going to go into general relativity for this video. From a Newtonian point of view, these masses are accelerating around one another, so they are not inertial observers. So let's take a look at the angular momentum from their point of view. We have our general definition for angular momentum. Let's say we take the point of view of mass 1. In this case, R1 is 0 because we're standing on M1. Since little r, our relative position is R2 minus R1, we have that R2 is just R. So the first term will go to 0, and the second term will just be R cross M times V, the relative velocity, giving us that the angular momentum from the point of view of mass 1 is just M2 times L, and little l, as we know, is constant. You can then do the same analysis from the point of mass 2. Now R2 is 0, and R1 is negative R, and substituting in, we find that the angular momentum from the point of view of mass 2 is just M1 times L. So even though these two bodies are not inertial observers, they still see the angular momentum is conserved. If you think about angular momentum and the force of gravity, this should not be a surprise, because the time rate of change of the angular momentum, which is the torque, is equal to r cross F. And the only force we have is the force of gravity. But the force of gravity points along the same line as r. And remember that the cross product takes the perpendicular component. So this is saying multiply r by the component of the force that's perpendicular to r. Well, there is no component perpendicular to r. R and F are parallel, therefore the torque on the system is zero, and if the torque is zero, angular momentum is conserved. So we've shown that for orbital motion, at least for a two-body system, angular momentum is conserved for all inertial frames, and both bodies will also observe the angular momentum of the other body to be conserved. But be careful here, if you're applying this to the solar system, this does not mean that from our point of view, all the planets have conserved angular momentum, because the planets cannot be treated as being in a two-body system with us. The Sun Earth can be treated as a two-body system, and so can the Earth Moon. But if you take the point of view of the Sun, then every planet can be treated as being in a two-body system with the Sun, because the Sun is so large that the gravitational forces between planets is pathetically minuscule and can be easily ignored, so each planet can be treated as a two-body system with the Sun. So from the point of view of the Sun, the angular momentum of every single planet is conserved. Yet another reason why it's useful to take the Sun's point of view and take on a heliocentric model. In the next video, we'll be looking at conservation of energy, and we'll be asking the same questions. Is it conserved? And if so, for which observers? So if you found this video useful and would like to see this next video on conservation of energy, be sure to like and subscribe, hit the bell to be notified for the release of future physics videos, and if you'd like to support the channel, you can check out my Ko-fi page, or you can just leave a super thanks. Thanks for watching, and I'll see you in the next one.